Very well. So we finish this chapter by talking about the resource allocation on the multi-axis channel, on the Gaussian multi-axis channel. What is resource allocation? Well, you have here the capacity region of the Gaussian multi-axis channel stated now in terms of transmit energy per symbol instead of received energy per symbol. So we define for ease of notation the gamma k is the transmit energy per symbol, which is equal to the received SNR divided by the channel gain when we normalize everything by the noise variance. So for simplicity, basically gamma k is simply ESK divided by N0 in the complex case, or gamma k is 2ESK divided by N0 in the real case. Okay? So why we use this normalization? Because we know that this capacity region depends only on the ratio of energy per symbol divided by N0, because as usual we can scale everything when the channel has this form. A scaling of the received signal does not change the capacity, and therefore we can always rescale the noise variance to be 1, and therefore the energy per symbol becomes this gamma k. So resource allocation means allocating the energy per symbol, so this gamma k, in order to operate at a given point of the rate region. So let me be a bit more explicit. So we have this rate region that in 2-dimension, let's do the 2-dimensional case just simply because it is easier to draw on the board. Otherwise, I have to draw a complicated multi-dimensional region, which is clearly not very convenient. So let's go to the 2-dimensional case. So we know that this region looks like this. So there is one rate constraint, let's say log of 1 plus, so here there will be G k gamma k, sorry, G1 gamma 1, this is the rate R1. Then there is another constraint, let's say this is here, so this will be log of 1 plus G2 gamma 2. And then there is a sum rate constraint, which is a line with the slope -1, and this will be basically the inequality R1 plus R2 less or equal than log of 1 plus G1 gamma 1 plus G2 gamma 2. Okay? Those are the corner points or successively decodable points. So suppose that we can shape this region by allocating the gammas, right? So suppose that we want to operate at a certain point. For example, we want to operate, let's say, at a point here. And suppose that we can, in fact, increase the power of user 2 and decrease the power of user 1, such that, for example, this point will be at a corner of a new region. So we are somehow shaping up the region in order to operate at a desired point. And in particular, it is convenient to make this point coincide with a successive decodable point, because we have already seen that successive decodable points are easy to implement, at least with the single user decoders. So this is a problem of resource allocation, where we allocate the powers in order to in order to achieve a certain desired rate point. And this rate point may be achieved, may be determined by some fairness criteria. For example, we may want to have all the users achieve the same rate. So in this case, there will be an equal rate point here, and then maybe we want to shape the region such that the region will somehow end up here, let's say like this. Okay, oopsie, they should be all parallel, these curves, like this. So maybe this rate is not as good as this one, but does not achieve a smaller sum rate, but for some reason we want all the users to use to achieve the same rate for fairness say conditions. So there may be several criteria. So this problem of shaping the capacity region in order to achieve a certain desired rate point is a problem of resource allocations, because in fact power and rate in the Gaussian case are related, and so allocating the powers, we are also allocating the rate, and allocating the rate means then operating with codes that achieve the desired rate point. So our problem is we have our capacity region, which is defined by this set of, we say, remember, we have 2 to the k minus 1 inequalities, okay? And the typical resource allocation problem consists of the so-called weighted sum rate maximization. Weighted sum rate maximization because our goal is to maximize a weighted sum of rates where these weights reflect some sort of priorities. For example, you may have different users. Each user is wants to or is ready to pay a certain amount of money per bit, or per bit per second, or per bit per symbol, which is called WK, and so maybe this reflects the total revenue of your system, right? So a user that has a big weight, WK is large, then you probably want to give to this user a large rate. A user that is stingy and wants to pay a small amount of money probably is going to receive a low rate. This is maybe a criterion. There are other reasons for which this weighted sum rate maximization makes sense. In fact, this problem of a weighted sum rate maximization can be incorporated in more complicated scheduling algorithms that would schedule rates over different rounds and recursively update the weights in a way that such that the long-term average rates of the user or the users will converge to some determined maximizing some desired fairness function. And these are there is a whole theory of scheduling, of fairness scheduling that maybe I will give a paper on in the end semester project about this, because it is in fact very interesting to see how you can incorporate very, very practical and very important scheduling algorithms in this framework. For example, there is an algorithm that is called proportional fairness scheduling, which is currently used in data-oriented transmission in 4G and 3G. And proportional fairness scheduling is a way of doing this sort of recursive update of these priority weights in order to achieve a certain long-term average performance. So our problem is maximize a weighted sum rate subject to the rate vector be inside the capacity region, and the capacity region is defined by these inequalities, and also subject to the sum power, the sum transmit power be less than sum total power, big gamma. Okay, so because this is a linear function, the objective function is linear, the capacity region is convex, and this constraint is also linear, this is a convex problem. What is the problem in this convex problem? Why we cannot just simply put it into a solver and get the solution? Because this region C is constrained by 2 to the k minus 1 inequality. So we have an exponential complexity in the number of constraints, which makes this problem very difficult to solve from first principle, say by using a general solver, for the simple reason that if I have, for example, 30 users, well, this region is defined by 2 to the 30 minus 1 inequalities, and you see immediately that even describing this region exhaustively is impossible, right? So, and scheduling 30 users is absolutely doable. It's done in cellular system today. A cell handles between, up to 60 or 100 users per sector. So this is commonly done. Okay. So you see immediately that if we are not smart, we cannot solve this problem easily. Okay. So how do we do this? Well, it turns out that the region C for the Gaussian case, so this region defined by these inequalities, has a very special structure, which is called a polymatroid structure. So polymatroids are special polytopes that appear in several combinatorial convex optimization and are defined in general as follows. So we define what is called a submodular rank function. What is a submodular rank function? Suppose that we have a set function given a set from 1 to k, so these are all the integers 1, 2, 3, 4 up to k. You know that the so-called power set of a set is the set of all possible subsets. And the power set contains all the subsets. So it's precisely what we have here, right? This calligraphic K is one possible subset of the set 1 to k, and we have one inequality for each subset. So basically, this function can be seen as a function of the subset. So a set function is a function that maps, so f, that maps the power set of a given set into the real numbers, okay? And in particular, here we are interested in the real non-negative numbers. So in other words, a function that associates to every subset of a given set a particular real number. Like, for example, this function is exactly like that, because for every calligraphic k, C of the sum over the set of these terms is a number and is non-negative because it's log of 1 plus this sum, okay? So this is we are exactly in this case. In addition, a set function is called a rank function or submodular rank function if it satisfies the following three properties. First of all, it's normalized. So f of the empty set is 0. And we are, in this case, because when the set is empty, we have C of 0. C of 0 is log of 1. Log of 1 is 0. So property number 1 is satisfied. Property number 2 is non-decreasing. So if we have a set K that contains a set K prime, f of k is larger or equal than f of k prime. So if we enlarge the set, the function can only, cannot decrease. And here is obviously the case, because if we increase the set k, then we have more non-negative terms in this sum. So we have log of 1 plus something bigger. Logarithm is a monotonically increasing function, and therefore the function increases. So we are in this case. And the last property is the most, let's say, complicated to check, is the submodularity. Submodularity can be stated as follows. given two subsets, k and k prime, f of k plus f of k prime is greater or equal than f of the union plus f of the intersection. Okay? So the submodularity is a sort of law of diminishing return. It can be expressed also in equivalently in an alternative way. If I have, oh Jesus Christ. They don't let me alone. They really don't let me alone. Okay. So basically, I was saying another way of expressing submodularity, let's call it 3 prime, is an equivalent condition. It's a bit difficult to show that the condition is equivalent, but it's something that you can try to do as a homework. It's a very good exercise. Is the following. Suppose that you have two sets, and then you have k, which is bigger than k prime. And then you have another element in, let's say, you have another element, let's call it b, that does not belong to set k. So in other words, you have a set k, a subset k prime, and then you have an external element b. But it turns out that f of k union b minus f of k is less or equal than f of k prime union b minus f of k prime. In other words, the variation of the function, if you augment a bigger set by an external element, is not larger than the variation of the function if you augment by the same element as a subset. That's why it's a law of diminishing return. Diminishing return means that if you make a little step starting from, if you're, law of diminishing return is something like this. If you make a little step here, you get a big variation. But if you make the same little step here, you have a much smaller variation. Oh, what happens? Jesus Christ. Okay, now I'm really fucked. Okay. Okay. So in a certain sense, this submodularity looks like a sort of concavity, but law of diminishing return. But in fact, it is applied to set functions. So the concept of concavity is not really relevant for set functions, and so we have submodularity. Okay, so suppose that we have such a function, and it turns out that our function c, which is log of 1 plus the sum inside a function, is satisfy exactly these three properties. Then a polymatroid is defined as the polyhedron in Rk plus, defined by the following inequalities. For every subset k in our ground set 1 to k, we have an inequality involving the variables in k, sum of the variables in k less or equal than the value of the function at set k. Okay? And the shape of a polymatroid is always like this. So this you may stretch it, it may be like you can deform it, but essentially the shape of a polymatroid is this sort of polytope that looks like a sort of diamond, and when you project this on every dimension, for example, you see always this pentagon. So you project it on the horizontal axis, you see a pentagon like this, right? Tack, 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 and tack. You project it on every dimension, you see a pentagon here. So in 2 dimensions, of course, we have just this. And and then in multiple dimension, when we go to higher dimensions, we can only imagine it by abstraction, because we cannot represent, not even using drawings in 4 dimension, 5 dimension, etc. So this is our polytope, which is defined by these inequalities, right? So we immediately recognize that because the function C of the sum of these non-negative terms is a set function with respect to the set over which we have the sum, you can identify these inequalities, and these inequalities have exactly the same shape, and it turns out that the function C is some modular rank function. So our capacity region of the Mach for the Gaussian channel is a polymatroid, okay? So how this polymatroid property is going to help us in solving our weighted sum rate maximization? Well, here is the main result that relates polymatroids and linear programming. So notice that a polymatroid is defined by linear inequalities, because a polytope is always defined by a bounding hyperplane. So it's a set of, is the intersection of half spaces. Each half space is defined by a hyperplane of the form sum over the x's equal to f of k. And so we have a set of linear inequalities, and we have to maximize a linear function, because this is a linear function of the rates. So this is a set of linear inequalities. So this is a linear program. Linear programs are easy, but as we know, linear programs, this is complicated because it has an exponential number of constraints. So here is the main result. The main result is that the solution of this problem, when we maximize over the rate for a fixed capacity region, is very easy. It is sufficient to take the permutation that sorts the weights in increasing order. So let pi be the permutation that sorts the weights in increasing order, or let's say non-decreasing order, because we have less or equal, less or equal. So we have this permutation, and then this permutation identifies the vertex of the dominant phase, so the vertex of the dominant phase, one of these points, that achieve the maximum of our linear function. So let me give you an example before so let's do the two-dimensional example. So suppose that we are in this situation. So we have our polymatroid in 2 dimension is simply this pentagon with. And now let's consider the following problem. So this is our region C, and then we have for max W1 R1 plus W2 R2 subject to the vector R1 R2 in C. Okay, so basically this is like saying take the line W1 R1 plus W2 R2 equal to constant, so equal to, for example, Z, okay, and then find the Z for which the line touches the boundary of this region. This is the maximum value of the sum, right, that satisfies the constraint. So what happens if, let's write this line in a slightly different way. Let's write it as R2 equal to minus W1, W2 over times R1 plus z. So you see that this is a line with slope minus the ratio of the weights. So what happens if W1 is larger than W2? This line will have a slope more negative than -1. So a slope that looks like this. This is slope -1. Okay. So this is the case W1 greater than W2. If W1 is smaller than W2, the slope is negative, but it is less negative than -1, and so this is the case W1 smaller than W2. Okay, so now you start translating this line. So z is the intercept with respect to the vertical axis here. You start translating this line, for example, in this case, as long it touches the region, and this is the maximum z you can get. In the other case, you translate this line until it touches the region, and this is the maximum you can get. So the optimal solution is either in this vertex, when W1 is less than W2, or in this vertex, when W1 is greater than W2. Okay? Now let's remember the successive interference cancellation connected with the vertices. This vertex, if you remember, was achieved by decoding first user 1, treating user 2 as noise, and then user 2 at its own individual capacity, because user 1 now is erased. So you see that this vertex corresponds to the decoding order 1, 2. And this vertex corresponds to exactly the opposite. You first decode user 2, treating user 1 as noise, and then user 1 at its own capacity level. So this vertex corresponds to the decoding order 2, 1. Okay? So now we see the rule, right? We see that if we sort the weights in increasing order, so in what was this? We sort the weights in increasing order, right? And then we start decoding in the same order in which in the sorting permutation. For example, in this case, the permutation is, well, in this case we have a W2 less than W1. So the permutation is pi 1 equal to 2, pi 2 equal to 1, and the decoding order is precisely pi 1, pi 2, so it's the order 2, 1, which is exactly what I have written here. In the other case, W1 is less than W2, the permutation is just the identity permutation, pi 1 equal to 1, pi 2 equal to 2, and again, the decoding order is pi 1, pi 2, which in this case is 1, 2, and this corresponds to the other vertex. Okay? So this is a general result that every vertex of the polymatroid corresponds to a permutation of the indices, and in our case, the optimum of this maximization problem is obtained by sorting the weights in increasing order, and then using the vertex point r pi, and r pi is the rate point corresponding to the vertex corresponding to the successive decoding order in order of the permutation pi. So you start decoding the user with the smallest weight, and you end up decoding at last the user with the largest weight. So the weights are in a certain sense priorities, And the user who is decoded first is disadvantaged because the decoder has to treat all the other users as interference. Then the second decoded user you have already subtracted the first, so has a little advantage. And you keep going like this until the last decoded user is the most favorable one, because we have already subtracted all the interference, and this is the one with the largest revenue, the largest weight. So that's more or less the intuition behind this result. So it turns out that you can write this vertex point exactly, because it's simply the component are simply given by the function C, calculated in the signal to interference plus noise ratio, right? Where at the numerator we have the user that we are decoding as step K, and at the denominator we have 1, which is the normalized variance of the noise, plus the sum of the variances of the residual interference signal, so the ones that are not yet decoding. So if we are decoding at step K, the not yet decoded users are the one from K plus 1 to big K. Okay? So this is the residual interference at step K. It turns out that if you write this function as log 1 plus this ratio, and then you multiply out, and then you break the logarithm into the difference of the logarithm of the ratio in the difference of two logarithms, and then you rearrange the terms, you can rewrite, and please do this as an exercise, you can rewrite the function in this form. Well, now we have that by construction, these differences are all non-negative, because we have used the sorting permutation. So W pi k is always greater or equal than W pi k minus 1. So those are all always greater or equal than 0. And these functions are logarithm of 1 plus, so they are concave. It turns out that this function at this point is a concave function of the gammas. And now we can maximize this function with respect to the gammas. And now we have a single constraint. So we have a linear constraint plus the non-negativity. And our objective function with respect to the gamma is a concave function. So we are maximizing a concave function over a linear constraint. This is a complex problem, and there are plenty of algorithms that achieve this problem. Unfortunately, you cannot really write the solution in closed form using, Lagrangian and stuff, but it's very easy at this point to obtain the maximum. Okay. So basically, we have obtained the maximum in 2 steps. The first step is to identify the vertex at which we want to work. So pose the problem for fixed gammas, just look at the rates, find the vertex, then we express the function, the weighted sum rate optimization at that vertex in terms of the gammas in this way. We see that it's a concave function of gammas, and now we have a very easy convex optimization problem to solve with respect to the gamma that can be solved by any suitable technique. Okay? Because now the problem is absolutely not complicated. There is nothing exponential. We have a single sum constraint here, plus individual non-negativity constraints. So we have essentially k plus 1 constraints, and then we have just a scalar maximization, a single concave function to maximize. So without this polymatroid idea, solving this power allocation problem over the Mach is very difficult. So this was a big breakthrough that makes the resource allocation over the Gaussian Mach very simple and tractable. As I say, there are plenty of algorithms that consider an outer loop that periodically update the priority weights of the W's, in order to achieve some sort of balance between the rates of the users in the long term over many scheduling slots, many scheduling rounds. And those are these fairness scheduling algorithms, among which proportional fairness scheduling that uses optimize a particular objective function is used in practical systems today. If I don't know if you have ever heard about something called EVDO. EVDO is enhanced data-oriented, something like that. I don't know. EVDO stands for what, but anyway, this was basically a way to somehow twist the so-called 3G systems in order to make them, instead of voice-oriented, data-oriented. And the big idea there was precisely to use proportional fair scheduling and give the schedule one user at a time and a cycle among the users using this proportional fair scheduling idea, which is essentially something that comes from this theory. And now, of course, this is used in plenty of LTE, etc., etc. Okay. So we can also work out an alternative problem, which consists in almost like the reverse question. Suppose that we want to solve the following. We are interested in supporting a set of target rates. So now our rates are fixed and are given, and we ask what is the minimum sum power to support these target rates. So in other words, the problem now becomes, I have a target rate point and I want to somehow shape the capacity region such that either I'm like this or I am, who knows, like this, right? But the sum power is minimized and the target rate is inside my capacity region. Okay? So this is another style of the problem. It's different, it's a different question. Before we wanted to maximize the rate for a given sum power. Now we want to minimize the sum power for a given rate. Okay? So it turns out that the problem has a similar solution. The problem has a similar solution. What happens? We can consider another set of another type of polytopes that are called contrapolymatroids, and so these contrapolymatroids are defined in the same way as polymatroid. The only thing is that now we have a supermodular rank function, and the supermodular rank function has the same properties 1 and 2, but property 3, called supermodularity, has the reverse inequality here. Submodularity, you have the where is it? F of k plus f of k prime is greater than f of the union plus f of the intersection, and for supermodularity we have the f of k prime is smaller than. And then the contrapolymatroid is a polyhedron defined by these inequalities. And now you see that also the sign here is reversed. So basically a contrapolymatroid has a typical shape of this form. It will be something like this. Okay, because now the inequality goes in the other way, so we in this case would be x1, so x1 greater than something, x2 greater than something, and x1 plus x2 greater than something. So we have, intersection of these half spaces. And the result here is that now we can restate restate the problem in the following way. So let's define the received powers. Received powers are simply the transmit powers times the channel gains, and we can reformulate the problem in terms of received power. So we minimize the sum of these ratios. These are the same as minimizing the sum of the gammas, subject to the received powers stay in the power region, the received power region that supports the rate tuple, the given rate tuple R1, Rk. And this power region is obtained by simply inverting the inequalities. So we have, the inequality of the type sum over set k of the rates less or equal than log of 1 plus sum over set k of the received powers. Now, if you invert these inequalities, you have this, right? And it turns out that this function, exponential of the sum minus 1, is precisely a supermodular rank function, and therefore this power region that supports a certain rate tuple is precisely a contrapolymatroid. So this region P of R for a given fixed rate tuple R is a contrapolymatroid in the powers, in the received powers. So our problem now is to minimize this weighted sum of received powers, where the weights here as 1 over the gains, 1 over the gains square are the weights. So minimize a weighted sum of received powers subject to the vector of received power being in the contrapolymatroid that describes the region of powers that supports a given fixed rate tuple. And so it turns out that the solution is very similar. So it turns out that the result of contrapolymatroid is that denote the permutation that sorts the weights in increasing order. So for which sorting the weights in increasing order where the weights are 1 over means also sorting the users in order of channel strength. So this means that user pi 1 has the largest gain, user pi 2 has the second largest gain. So this will be the strongest user first, second strongest user, and then the weakest user is the last. And then it turns out that the sum power is minimized by the vertex p sub pi obtained by decoding again in the same order. So here you decode the decoding order that minimizes the sum power, decodes the strongest user first, the second strongest user second, and so on and so forth. Which in a certain sense makes sense if you think, imagine to receive the superposition of all these users, and then you try to decode the strongest by treating the other who are weaker as interference, then you subtract the strongest, you keep going like this. In this way, you spend the least amount of power for a given set of rates. So plugging in the solution, we end up with this solution in terms of received powers, and of course these are function of the rates. And then at this point, we can simply obtain the corresponding minimum transmit sum power by simply replacing these solutions inside the weighted sum power. So we are going to have this. So in other words, the power required by user k is going, so this gamma k is going to be this formula that of course is a function of the rates. It's a function of this sorting permutation. Okay, so we have basically two elegant solutions, and here we end the chapter. Two elegant solutions to the two very interesting resource allocation problems. One is maximize a weighted sum of rate subject to a sum power constraint, The other one is minimize the sum power subject to a given set of target rates. Okay? And the key idea here to solve these problems is to exploit this structure of polymatroid and contrapolymatroid that have these important results, for which by simply sorting the weights of the linear function you want to maximize or minimize in the two different cases, you identify immediately the vertex at which this minimum or maximum appears. So this avoids this exponential number of constraints because it gives you directly the solution. Okay, so this ends what I wanted to say about the multi-access channel, and in particular the Gaussian k-user multi-access channel and the corresponding resource allocation over the Gaussian multi-access channel.